Now we're going to turn to marginal product. This is probably the top concepts we're going to cover in this chapter. It's what underlies cost minimization, which we'll do towards the end of the lecture. And it's what ultimately underlies economic thinking of producers, right? They're thinking on the margin of how to best optimize their production process. And the focus is going to be on that marginal product of each of their inputs. So how much to total output does an additional worker add, or how much to output does an additional capital good add, right? An additional machine. So formally, we can generalize this definition by saying that marginal product is the additional output that a firm can produce by using an additional unit of an input, holding the use of the other input constant, right? So here again, we have that ceteris paribus assumption. Right? We want to see how changing one input by one unit impacts output in order to identify its full effect. So again, this is the ceteris paribus assumption. Okay. Generally, we assume, like I mentioned in the first video, that as more of an input is used, output falls. So not output falls, but the increase of output is less. So this is what we call diminishing marginal product. So our first person we hire to work for us is assumed to be more productive than the 10th person hired, right? And it has to do with how we conceive of our production function, right? So we talked about it when we have a Cobb-Douglas production function, like we have here on the slide. If we have no workers, there's no output being made. So when we jump from no workers to one worker, that's a huge bump in production, right? If we go from one worker to two workers, that's going to increase output again, but by less than that first worker did. So that's our diminishing marginal product. And we can trace out that effect. So to find marginal product, we're going to use what's called a partial derivative. So if you don't remember your derivative rules, I invite you to review those. But basically, a partial derivative is very straightforward in that you apply the derivative rules like you would normally, but you only apply them to one of the variables at a time. Okay, so let's take an example. So if we have y equal to, let's say, 5x plus 3, we want to know what is the derivative of y with respect to x. Here, we're going to say, okay, x has a 1 exponent. We're going to apply the power rule. So we'll have 1 times 5, it left in our derivative. Then we're going to subtract 1 from that exponent. X is now going to have a 0 exponent, which means x is going to go to 1. So we'll have 5 times 1 plus here, there's no x modifying the 3, so that's going to go to 0, right? 3 doesn't change with x. It's a constant, it stays the same. So our derivative of y with respect to x is just 5. Okay. We can do another example. So y is equal to, let's say, 2x squared plus 10, right? If we take that derivative of y with respect to x, we're again going to apply that power rule. So 2 times 2 is going to give us 4. We're going to subtract 1 from the exponent, and we're left with x to the 1 power. 10 is not modified by x. It's a constant. It doesn't change with x. So that change is going to be 0. So we're left with the derivative of y with respect to x being 4x. Okay, so that's an overview of the power rule. Now we're going to apply it when there are multiple variables and we take a partial derivative. Okay, so let me just clear these annotations real quick. All right, so let's say now we have y is equal to 2x squared plus 3z plus 5. And I want to know, how does y change when only x changes? And you'll note in my notation here that I'm using a delta rather than a d. Okay, that signifies to the reader that we're doing a partial derivative. So that's not a 2, that's a delta. Okay, so we're going to only look at how x changes, and we're going to pretend as if this Z here is a constant just like R5, right? So starting with our first term, we have an X, so we'll apply that power rule. So we'll have 2 times 2, that gives us 4. Subtract 1 from that exponent on X, that gives us X to the 1 power. Plus, now our second term, we have Z, a variable, but it's not X. So Z does not change as X changes. So this we're treating as a constant, it's going to go to 0. Just like 5 doesn't change with X, it's going to go to 0. So we'll have 4X plus 0. So our partial derivative here is 4X. We could do the same for Z. Right? So if we want to see how Y changes when Z changes, let me erase all these additional annotations to our equation here. Okay, so now we're going to treat X as if it's the same as that 5, and we're going to focus on how Y changes when only Z changes. So 2x squared, it's a variable, but there's no Z. So we're treating that like a constant. It goes to 0. Z in our second term here is present, and it has a 1 exponent. So we're going to multiply that exponent by its constant. So we'll have 3Z, or excuse me, 3. And then we're going to subtract 1 from that exponent on Z. So we'll get Z to the 0, which means Z goes to 1. Right? So we're left with 3 times 1. And then lastly, that 5 is a constant. It doesn't change with Z, so it goes to 0. So the partial derivative of Y with respect to Z is 3. Okay, so those are some examples. Let's look now at the type of example you might see in this class for production functions. So let me see if I can, that did not work. Okay. What did I do? There we go. All right, so let me erase this math that I just did. And we'll look at another example. Again, one that is going to be similar to what you're going to see in class. So if we have a production function of output equal to K to the 1/2 power plus L to the 1/2 power, and let's say I want to find the marginal product of labor. So how output changes when only labor changes, right? So that's why we use that partial derivative. We want to hold K constant. Oh, excuse me, this shouldn't be a plus, that should be multiplied. So our production function is Q equal to K to the 1/2 times L to the 1/2, right? So when we have our variables multiplied by this, like this, it's going to be a little different than our examples we just previously did, but we're still going to treat K as a constant. So just pretend it's like the number 5, all right? So we have 1/2 in our exponent for labor, and we're going to multiply that by the constant on L, which is K to the 1/2 power. So we'll have 1/2 times K to the 1/2 power. Then we're going to subtract 1 from L, and 1 from the exponent on L. So we'll have 1/2 minus 1, which leaves us with L to the negative 1/2 power, right? Which is similar, you can see, to the general example I've included on the slide. We're going to take a look at that negative exponent on L and go ahead and move that to the denominator. So we'll have K to the 1/2 power all over to the L times, excuse me, raised to the 1/2 power. So K to the 1/2 power over 2 times L to the 1/2 power, and that is the marginal product of labor. Now let's do the marginal product of capital. Here we want to see, how does output change when only capital changes, all right? So now capital is our variable, and we're going to treat L as a constant. So we can say that this is like the number 5, all right? So we'll have 1/2, that exponent on K, times the constant modifying K, which is L to the 1/2. So we'll have 1/2 times L to the 1/2 power times capital, right? After we subtract 1 from its exponent. So we have capital to the negative 1/2 power. Because we have that negative exponent, we can rewrite this equation like we did the previous one, where we move capital to that denominator. So we'll have L to the 1/2 power all over K times 2, 2 times K to the 1/2 power. So marginal product of capital is L to the 1/2 power over 2 times K to the 1/2 power, all right? So now that we have solved for our specific marginal products of labor and capital, let's see if we can identify the diminishing marginal product within these formulations, right? So if we think first about marginal product of labor, that again is how much additional output a firm produces with an additional unit of labor, with an additional worker. So if we look at the equation for marginal product of labor, labor is in the denominator. So as labor grows, the value of marginal product of labor overall is going to fall, right? As L goes from being 1 to 10, right now that value is much smaller, okay? For example, if we have capital, let's say that capital equals 10 initially and labor equals 1, we're going to have, excuse me, not 10, let's do 9. Capital equals 9, so we'll have marginal product of labor is equal to 9 to the 1/2 power, all over 2 times 1 to the 1/2 power. We're going to get 3 over 2 times 1, so we'll get 3/2, right, 1.5. If instead we're looking at our 10th laborer, or let's not do 10th, let's do 4th laborer. We have capital, right, still 9 times 9 to the 1/2 power, all over 2 times 4. Now we're looking at the 4th laborer to the 1/2 power. That's going to get us 3 over 2 times 2, so 3/4, and now we're at 0.75, right? So as that denominator grows, our value of, in this case, marginal product of labor overall falls. This is going to also be true for our marginal product of capital. Capital is in the denominator, so as more capital is used, the marginal product of capital is going to fall, right? Just like we saw with marginal product of labor. Okay. I want to give you another example here. This one hopefully will help you see the intuition in the math. So let's say that we own and operate a fry shop, right? They only make fries, specialty fries, and we're going to call it Fry Supply. And we have some capital here. We have a fry station, but we can't make any fries without hiring anyone. Without hiring anyone. So we hire our first worker, right? The pimply-based team. He's going to operate our fry station. Adding him increases our output enormously, right? Previously, we were making no fries. Now we're making a bunch. We say, okay, pimply-faced team, he's doing a good job. He's not the most skilled worker, so we're going to let him focus on 1/2 of this fry station and hire someone else to do the other half. Right now, we've boosted our output even more. Our second worker is not as productive as our first because he didn't take us from 0 to positive amount, but he's still adding positively. So we say, okay, let's add another guy. Right now, they can more or less each focus on their own fry basket. So we'll add one more so that each can just really focus on getting the perfect fry on our potatoes. And we say, okay, with each of these laborers we've hired, our output has gone up, right? It's not going up at the same rate, but it's still moving upward. So maybe we should give these guys some more support. So we keep hiring workers to help out their buddies here. And pretty soon we end up with too many cooks in the kitchen. They're elbowing each other to get access to that fry station. One ends up in our fry basket and we have a new thing on the menu, right? So there is a point where in adding inputs and adding laborers, we're not getting much of a return, right? There's a certain point where those returns flatten out and potentially pushed far enough can become negative. So the only way that we could increase our output really meaningfully again, once we have this many workers, is by adding another fry station, by changing capital, right? But then we have a change in both labor and capital and not just the change in the one, right? So we'll see that with returns to scale, how if we change both inputs, what that means for our production function for output. But for a marginal product, we're going to stop here. And then in the next video, we'll turn to short run production.